use a diagram, okay, to visualize the computation process. Okay. Now initially, okay, we push the pointer to node A into the queue. Okay. Now this is the initial condition, and then we enter into the while loop. Now usually the control of the while loop in this case will be as long as the queue is not empty. Now the queue is not empty means that there are some nodes in the tree that is not yet visited. Okay, so we need to do some computations, okay, related to the subtrees that we save in the queue. Okay. Now as long as the queue is not empty, we enter into the while loop. Okay, we take out the front element. Okay, now we take out the pointer. Okay, in the front of the queue. Now we are referencing, okay, node A. Okay, and then we will, okay, visit that node. Afterwards, we check if its left pointer is null or not. If its left pointer is not null, we push its left pointers into the queue. Now, in the queue, we have the pointers to B. Okay. And then we check if the node P, the right pointer is null or not. If it's not null, then we push the pointers to X into the queue. Okay. Then we come back to the while loop, the beginning of the while loop. Okay. Now as long as the queue is not empty, we take out the first item. And now the variable P is pointing to node B. Okay? We output the node label. If the left pointer of B is not null, we push it onto the queue. The right pointer is null, nothing. So we don't push a null pointer into the queue. Okay. Then we come back to the while loop. Okay. So this time we take out the first item. Okay. And in this case, P is now pointing to node X. And once again, okay, we push its left and right pointers into the queue. Okay. Then we come back to the loop, and the next pointer we retrieve, you will see. Okay, now you see that we are going to visit the nodes in the tree level by level, on each level, left to right. Now, to preserve that left to right traversal in a level is based on the order of these two push. You always push the left pointer, if it's not null, before pushing the right pointer. Now Q is a first in, first out data structures. Okay, so in this case, by doing the push in that order, then you guarantee that later when you visit the left and right child of the same parent, you will first visit his left child before the right child. Now this is the invariant properties that we maintain in the loop. Now, so far you may wonder, well, you have some traversal order and blah blah blah, and so what? Okay. Let's see. Before we take a look at other operations, let's see one. Okay, example application first. Okay, and then you will appreciate. The definition of those different traversal orders. Now, we have done some exercise on expressions, right? Arithmetic expressions. Now, we can also represent an arithmetic expressions using a binary tree. Okay, now this is one example. Now in the representation, okay, we have an operator. All operators are internal nodes of the binary trees. Okay, and the operators operate on the two operands, okay, that are the value represented by his left subtree and the right subtree. Now if the left and right childs are operands, okay, then they are the two operands. Now if the left child or right child is an operator, then it means that the left operand is to be produced by the corresponding operator. Okay. Now, the this is the infix expression. Okay. These expressions can be represented by this binary tree. Okay, so we will perform 6 minus 7 multiplied by 4. Now 4 multiplied bracket 6 minus 7 divide by 5. Now this is this term. Okay. Add 3. Now this is the left hand side. Okay. This is the left hand side. Add 3. And then finally, you have the other add 3. Okay. Now, if we have the binary tree representation of an arithmetic expression, and we want to evaluate, okay, the values. This is the internal representation of the expressions in your program. Okay, so how are you going to do the evaluation? Now, the evaluation will be based on a post-order traversal of the tree. Okay. Now, every time before you evaluate an operator, you need to have the results of his two subtrees. Now, if we are going to traverse the tree in post order, okay, first we get 3. Okay, so we return the value 3 to this addition operator. But before we can evaluate the addition operators, we need to evaluate its right subtree. Okay. Now, before we can evaluate the division operator, we need to evaluate its two subtree. Now, evaluating its left subtree is the multiplication operator. We evaluate the left subtree is an operand, so we receive a value 4. Okay. And before we can evaluate the multiplication, we evaluate the right subtree. So 6 plus 7, it will return a value of 13. Okay. Now we have 4 and 13. Then we can compute 4 times 13, returns a value of 52. Okay. Then you have the value 5. Okay. Now 52 divided by 5 is 10.4. Okay. Now you have the return value 10.4 plus 3. Now you have 13.4. With 3, and then the final answer is 16.4. Now actually, in the old days, a compiler, when people type your, okay, expressions, computations, involving okay, this kind of arithmetic expressions. The compilers use this kind of, okay, translate your programs into this kind of internal representations and then produce the machine code, okay, for the actual evaluation. Now, in this example, okay, we define the data type, okay, that we need to store in a node. Okay. Now, in the data type we store in a node, it can be an operator, or it can be a double precision value. Okay. Now, in a node, it can be a number, an operand, or it can be an operator. Okay. And in this example, okay, we use a union. Okay, what is a union? A union means that in the physical memory structures, okay, you can either store a operator or a value. Okay, it means that the amount of memory space allocated is the union of the two. Okay, that is the larger size of the two. Okay, so it will be 8 bytes. Okay, because a double requires 8 bytes. A character requires 1 byte. And but we don't need to have a total of 9 bytes because it's a union. And then there's a control variable. Okay, the control variable is a data type. Okay, it can be a character. So data type here will tell us, okay, the information that we store here. Is this an operator or is it an operand? Okay, but we cannot store both, okay, operator and operand at the same time because it is mutually exclusive. Now to perform the evaluation, okay, the algorithm is based on post-order traversal. Now you are receiving a pointer to a node. Okay. Now when you evaluate an expression, then the precondition of this